All right, today we're going to talk about what an improper integral is called. So an improper integral is an integral where one or both of the limits of integration are infinite. And the other option is that there's an infinite discontinuity, in other words, a vertical asymptote, and that can be on the limit itself, or it can be between the limits. So here's some examples, and I'll kind of explain why these have to be. Well, actually, you know what? Look at that definition, pause this video really quick, and you decide on 5, 6, 7, and 8, decide why they are improper integrals. So number 5 is an improper integral, right? Because it has a limit. One of its limits goes to infinity. On 6, they both do. One side goes to negative infinity, one side goes to positive infinity. On 7, right, neither of the limits go to infinity, but if you look on the interval, right, the interval is from 1 to 5, we know that there's a vertical asymptote at x equals 1. So that's that second thing up above, right? It says if there's an infinite discontinuity. Same thing on 8, right? The limits go from -2 to 2, but there is a vertical asymptote at x equals -1, which is on that interval. So that's why each of them are considered to be improper integrals. Okay, so let's see how a couple of these works. So if you look at example number 9, it says the limit of 1 to infinity of 1 over x squared dx. So the whole idea here is this, is we are starting at 1 right here. And we're trying to find the area as it goes to infinity. And sometimes that's confusing. We want to ask ourselves, like, well, how could it, we know that 1 over x squared gets closer and closer. It has a horizontal asymptote at y equals 0, so it gets closer and closer to there. And if we go on forever, there'll be an infinite amount of area, but that area approaches a certain number. And so as we go to infinity, we can actually find out what that number is. So that's what's happening here when we evaluate this improper integral. So the way we do it is this, is I rewrite this definite integral. I write it as being the limit as b approaches infinity of the definite integral from 1 to b of 1 over x squared. So all we've done is replace the infinity sign with a b, and out in front we put the limit as b goes to infinity. So we're just saying what happens to the areas as b gets bigger and bigger. Okay, well what that allows us to do is now we can just integrate that like we normally would. So I have the limit as b approaches infinity. I'm going to integrate x, right? This is just x to the -2 dx. That's what I'm integrating right there, right? So it'd be x to the -1 divided by -1, and I'm going from 1 to b. I'm going to plug now in my upper limit, so I'm going to plug in b, and I end up with the limit as b goes to infinity of -1 over b minus, and then plug 1 in to be minus a -1, so that ends up being a +1. Okay, now just evaluate this. What happens as b goes to infinity? Well, this part right here, right, as b gets bigger and bigger, that part's going to go to 0. So you end up with this equals 0 plus 1, or my answer is just 1. So kind of cool what happens, again, this area, as I start at 1 and go to infinity, is equal to 1. And what would happen if you looked on a calculator and you could find that areas, you know, with different upper limits, you'd say it gets closer and closer and closer to 1. And as you go to infinity, it does equal 1. When that happens, we say that the function converges. Okay, so the infinite limits exist, or these limits, these improper integrals, they exist, they have an answer. If the limit, as you approach the limit, is a finite number, it comes out, like for example, that one came out to be 1, we say that it converges. If it does not equal a finite number, you know, the limit doesn't exist, then we say that it diverges, and then there's no answer. We just leave it at that it diverges. We'll look at number 10. Number 10 is actually an example of one that diverges. Okay. So we set it up the same way, though. We're just going to say the limit as b approaches infinity of definite integral from 1 to b of 1 over x dx. Okay, so we're going to integrate that. So we get the limit as b approaches infinity of the ln of the absolute value of x. We're evaluating it from 1 to b. So I end up with the limit as b approaches infinity of the ln of b minus the ln of 1. Well, what happens is b goes to infinity. The ln of b goes to infinity. This is just 0. Anyway, but it goes to infinity. It doesn't approach a finite number. What we say then is that it diverges. We just have to leave it at that. So if it converges, we have an answer, right? Over here, the area came out to be 1. If it diverges, it just means the area is going to keep getting bigger and bigger. It's not going to approach a number. Okay, let's look at number 11. So again, set it up the same way. It'll be the limit as b approaches infinity of the definite integral from 0 to b of the cosine of x dx. We integrate that. We end up with the limit as b approaches infinity of the sine of x. Plug in b. The limit as b approaches infinity. Well, what happens here, right? As b gets bigger and bigger, we know what happens, right? The sine function goes like this, right? So my answer just oscillates between -1 and 1. It does not approach a finite number. This is just 0 over here, so we don't have to worry about it. So because it doesn't approach a finite number, we again just say it diverges. Okay, you guys are going to love this next one. It's awesome. So we have the definite integral from 1 to infinity of x e to the negative x. Our first step's still the same. The limit as b approaches infinity of 1 to b x e to the negative x dx. What's cool about this one is not only do we get to evaluate an improper integral, we also get to do integration by parts. This is a good review. So like x times e to the negative x, we can't integrate any other way. So I'm going to say u is equal to x and dv is equal to e to the negative x. That means du would be dx. And v, if I integrate e to the negative x, I just end up with a negative e to the negative x when I integrate that. I should have put a dx up there. Okay, let's go ahead and use ultraviolet voodoo, right? So it's u times v, so I have the limit as b approaches infinity of, and it's u times v, so it'd be x times negative e to the negative x, minus the definite integral of, and this is the voodoo part, right? So I take v, negative e to the negative x, times du, which is dx. And I have to evaluate this all from 1 to b. I'm going to just finish this off by taking that definite integral right there before I go on. So I have the limit as b approaches infinity of negative x e to the negative x. The minus and the negative can cancel out, but then when you integrate it, you end up with another negative. So we end up with a minus e to the negative x. Okay, now I got to plug in b and 1. So I have the limit as b approaches infinity. When I plug in b, I end up with a negative b over e to the b minus 1 over e to the b minus, I got to plug in the 1, so that would be negative 1 over e to the 1, so negative e 1 over e. Plug 1 in the next one, you get minus 1 over e. Okay, think about what happens here. As b goes to infinity, the denominator goes to infinity, which means this gets closer to 0. Same thing happens here. So both of those go to 0. This ends up being plus, what, 2 over e? So there's my answer. So the area under the curve from 1 to infinity of x e to the negative x dx comes out to just be 2 over e. Love that problem. Get to do some an improper integral along with also integration by parts. Okay, I'm going to erase that really quick, and then we'll look at this last example. So just a heads up in this last example, if you notice, if you look at the limits, the limit, there is no infinity sign up there. But we should also notice this is still an improper integral, and the reason why is because there's a vertical asymptote, right? At x equals 0. We know that x cannot equal 0. There's a vertical asymptote there. So when that happens, this is how we have to approach it. We actually have to break it up. So what I do is I take the limit as b approaches 0 from the negative side, and I'll show you why here in just a second, of the definite integral from, we're going to go from -1 to b of, x to the -3 dx, plus the definite integral from, we're going to go a to 2. So what I really did is broke it up at x equals 0, where the vertical asymptote is. I broke it up. If you want to think of it as this was being a 0 and this being a 0, we break it up right there. And because there's a vertical asymptote of 0, I have to replace that 0 with something else. And that's why I replaced it with a b right here. Right? And on this one, I replaced this 0 down there with the a down here. Oh, I forgot my limit in there. I'm sorry. Let me just fix that really quick. So the second part would be the limit as a approaches 0, this time from the positive side of, we're going from a to 2. So really you're just splitting that definite integral in half. Now the reason why we're approaching it, right, if I'm going from -1 to b, think of a number line, right? Here's -1, and b was for 0. I'm coming from -1 to there. I'm approaching from the left side. On the second one, I have 2 over here as the upper limit, and I'm approaching 0 from the other side. So I'd say 0 from the, so that's how we go from the negative side when I'm going -1 to 0. When I'm going 2 to 0, I'm coming from the positive side. So that's why I have that approaching from the left and approaching from the right. Okay, let's evaluate these now. So on that first one, I have the limit as b approaches 0 from the left of, let's see, add 1, x to the -2 over -2, going from -1 to b, plus the limit as a approaches 0 from the positive side of x -2 over -2. We're going from a to 2. All right, so we end up with this, the limit as we approach b from the negative side of, let's see, 1 over -2b squared, plus plug -1 in there, and you end up with, it's minus a -1/2 or plus a half. Okay, plus the limit as you approach a from the positive side. Plug 2 in first, and you end up with a -1/8. Okay, and then plug a in, you end up with a minus 1 over 2a, -1 over 2a squared, and it's being a plus 1 over. Okay, just to evaluate that. So look what happens on this part. As you approach 0 right here, the denominator will get smaller and smaller, which means 1 divided by smaller and smaller numbers, you're going to end up getting bigger and bigger. So that goes to infinity. The same thing happens over here. It also goes to infinity. It doesn't matter that if it's one of the two goes to infinity, then the answer is it diverges. In this case, they both do. So we say it diverges, which means we don't have an actual finite answer there. Okay, so that is your lesson on improper integrals.